In this video, we are going to learn how to establish trigonometric identities. Now, this is part one of a two-part video lesson, so be sure to, after you watch part one, to go and watch part two as well. Now, we learned in the last lesson that we can use algebra to simplify these trigonometric expressions, and then sometimes we'll learn that something will simplify to a very simple trig function, and there are a lot of these that will happen. So we call this an identity when sometimes it simplifies into something as just one trig function. So what establishing an identity is I give you an identity, and then you must go from one end of that equation to the other and show me why they are equal. So I'm going to start with the more complicated side, cosecant theta times tangent theta, and I'm going to show you why it's equal to secant. So I'm basically going to remove that part from the equation, and I'm going to show you all the steps it takes to get there. Now, one technique we can use when we simplify is we can switch everything to sines and cosines. So we're going to use the reciprocal and quotient identity, which is cosecant of theta is equal to 1 over sine of theta, and tangent of theta is equal to sine of theta over cosine of theta. So this can be rewritten as 1 over sine of theta times sine of theta over cosine of theta, using the reciprocal identity and the quotient identity. Now that I'm here, I can see, oh, the sines can cancel, and I'll be left with 1 over cosine of theta, which is another reciprocal identity, because I go from here to here, I know that 1 over cosine of theta is equal to secant of theta. That's the other reciprocal identity that I didn't use here. That gives me secant of theta. Now I've shown the pathway to go from cosecant theta tangent theta all the way to secant theta. So I've now confirmed that this is true, therefore I've established that identity. Let's try with another one. Here I have sine squared of negative theta plus cosine squared of negative theta is equal to 1. Now I know the Pythagorean identity. It is sine squared of theta plus cosine squared of theta equals 1. But that is theta, not negative theta. Now there could be arguments made that as long as the angles are the same, this works. And that could be a proof for another day. But now I just want them to show the thetas so I can say that this is equal to 1, like I'm saying here. So what I'm going to do is use the even odd properties to figure this out. So I'm dealing with sine of negative theta and cosine of negative theta. Sine of negative theta is negative sine of theta, and cosine of negative theta is just cosine of theta. So now I can rewrite these as negative sine of theta squared, all of that squared, plus cosine of theta squared. But now I'm squaring a negative, so it remains positive. So now I have sine squared of theta plus cosine squared of theta, which now we know for sure that is equal to 1. So now we've shown that this identity is definitely equal to 1. Next up, we have a very similar situation with the even odd properties, but we don't have that plus in the middle, so we know that that top cannot equal 1. But what we're going to find out soon is that this entire expression equals cosine of theta minus sine of theta. So let's work through why that is, because it doesn't seem like it would simplify to something so nice. So let's start here. I have sine of negative theta squared minus cosine of negative theta squared all over sine of negative theta minus cosine of negative theta. Now using these even odd properties, I can rewrite this as negative sine of theta minus negative sine of theta squared minus cosine of theta squared all over negative sine of theta minus cosine of theta. So that this term became negative because the negative came out, but here the negative didn't come out, so it remains negative. Now I have sine squared of theta, because again the square got rid of that negative in front, minus cosine squared of theta all over, and I'm just going to factor out a negative, times sine of theta plus cosine of theta. Now I have two squares being subtracted. That is difference of squares. So if I thought of that top part as x squared minus y squared, with x equal to sine of theta and y equal to cosine of theta, that could just be rewritten as x plus y times x minus y, the difference of squares, which gives me sine of theta plus cosine of theta times sine of theta minus cosine of theta all over negative of sine theta plus cosine theta. You'll see here we have a common factor, leaving me with sine of theta minus cosine of theta all over negative 1, which that's sine of theta minus cosine theta, but now that I'm divided by negative 1, that's now negative sine and positive cosine, leading me to cosine of theta minus sine of theta. And again, it took a while to show it, but now I've proven that this big expression can always be replaced by this smaller expression. Now lastly, I have 1 plus tangent of u over 1 plus cotangent of u. Now here, I'm not going to use sines and cosines, only because cotangent is actually the reciprocal of tangent, and I can reduce this down just to one trig function very quickly. Because I know that cotangent of u is equal to 1 over tangent of u. So this can be rewritten as, and that is the reciprocal identity, 1 plus tangent of u all over 1 plus 1 over tangent of u. And now we're dealing with a complex fraction. That's a fraction within a fraction. And one way you can handle this situation is to multiply the numerator and the denominator of the bigger fraction by the denominators within the fraction. So this denominator here, tangent of u, if I multiply the entire denominator by tangent of u, it will cancel that out. But in order to keep this to be equal to the same fraction, I must also multiply my numerator by tangent of u. This will leave me with 1 plus tangent of u times tangent of u. I'm just not going to distribute yet. In the denominator, I'll distribute this one, that'll be tangent of u. And this tangents will cancel, plus 1. You'll notice here that the 1 plus tangent of u and tangent of u plus 1 are the same. They can cancel, and I'll be left with just tangent of u, which was what my goal was in the first place. So this expression can be replaced with just tangent of u. Now that concludes part 1 of establishing trigonometric identities.